Bitter criticism. We have a physics news, a news about physics. Again, this came to me on social media on Facebook, but I like, I have to recognize I'm not good at physics as everybody have. But I guess this is just a matter of bad teaching, bad teaching, bad pedagogy, I guess. Anyway, phys.org. First coherent picture of an atomic nucleus made of quarks and gluons. I don't know what's gluons. I never heard about it. By Polish Academy of Sciences. And we have a photograph. For the first time, quarks and gluons were used to describe properties of atomic nuclei, which until now had been explained by the existence of protons and neutrons. The temporary pair of correlated nucleons is highlighted in purple. The atomic nucleus is made up of protons and neutrons, particles that exist through the interaction of quarks bonded by gluons. It will seem, therefore, that it should not be difficult to reproduce all the properties of atomic nuclei, either to observe in nuclear experiments using only quarks and gluons. However, it is only now that an international team of physicists has succeeded in doing this. It's been almost a century since the discovery of the main components of atomic nuclei, protons and neutrons. Initially, the new particles were considered indivisible. In the 1960s, however, there was a suggestion that at sufficiently high energies, protons and neutrons will reveal their internal structure. The presence of quarks constantly held together by gluons. Soon afterwards, the existence of quarks was confirmed experimentally. It may therefore seem surprising that, despite the passage of many decades, no one has been able to reproduce with quark-gluons models the results of nuclear experiments at low energies, when only protons and neutrons are visible in atomic nuclei. This long-standing deadlock has only now been broken. In a paper published in Physical Review Letters, its main authors are scientists from the international NCTEK collaboration on quark-gluon distributions. Quote, until now, there have been two parallel descriptions of atomic nuclei, one based on protons and neutrons, which we can see at low energies, and another for high energies, based on quarks and gluons. In our work, we have managed to bring these two so far separated worlds together, says Dr. Alexander Kusina, one of the three theoreticians from the nuclear physics of the Polish Academy of Sciences, IFGPAN, participating in the research. Humans see their surroundings because they use innate detectors, eyes, to register scattered protons that have previously interacted with the atoms and molecules that make up the objects of our environment. Physicists gain knowledge of atomic nuclei in a similar way. They collide them with smaller particles and meticulously analyze the results of the collisions. For practical reasons, however, they use not electrically neutral protons, but elementary particles carrying a charge, usually electrons. Experiments then show that when electrons have relatively low energy, atomic nuclei behave as if they were made of nucleons, that's it, protons and neutrons. Whereas at high energies, partons, that's it, quarks and gluons, are visible inside the atomic nuclei. The results of colliding atomic nuclei with electrons have been reproduced quite well, using models assuming the existence of nucleons alone to describe low energy collisions and partons alone for high energy collisions. However, so far these two descriptions have not been able to combine it into a coherent picture. In their work, physicists from the IFJPAN use data on high energy collisions, including those collected at the LHC accelerator at CERN laboratory in Geneva. The main objective was to study the partonic structure of atomic nuclei at high energies, currently described by parton distribution functions, PDFs. Parton distribution functions, PDFs. These functions are used to map how quarks and gluons are distributed inside protons and neutrons and throughout the atomic nucleus with PDF functions for the atomic nucleus. It is possible to determine experimentally measurable parameters such as the probability of a specific particle being created in an electron or proton collision with the nucleus. From the theoretical point of view, the essence of the innovation proposed in this paper was the skillful extension of parton distribution functions, inspired by those nuclear models used to describe low-energy collisions, where protons and neutrons were assumed to combine into strongly interacting pairs of nucleons, proton-neutron, proton-proton, and neutron-neutron. The novel approach allowed the researchers to determine for the 18 atomic nuclei studied parton distribution functions in atomic nuclei, parton distribution in correlated nucleon pairs, and even the number of such correlated pairs. The results confirm the observation known from low-energy experiments that most correlated pairs are proton-neutron pairs. This result is particularly interesting for heavy nuclei, for example, gold or lead. Another advance of the approach proposed in this paper is that it provides a better description of the experimental data than the traditional method used to determine parton distributions in atomic nuclei. Quote, in our model, we made improvements to simulate the phenomenon of pairing of certain nucleons. This because we recognize that this effect could also be relevant at the parton level. Interestingly, this allowed for conceptual simplification of the theoretical description, which should in the future enable us to study parton distributions for individual atomic nuclei more precisely, explains Dr. Kusina. The agreement between theoretical predictions and experimental data means that using the parton model and data from the high energy region, it has been possible for the first time to reproduce the behavior of atomic nuclei so far explained solely by nucleonic description and data from low energy collisions. The results of the described studies open up new perspectives for a better understanding of the structure of the atomic nucleus, unifying its high and low energy aspects.